For the first time in the history of earthquake science, artificial intelligence just caught the San Andreas Fault doing something no human researcher had ever managed to fully see before. Not a big earthquake, something quieter, something hidden inside decades of data that scientists had been staring at for years without ever noticing the pattern buried underneath. And what that pattern reveals is genuinely reshaping how researchers think about the most famous, most closely watched fault line in North America. Let's start with the location where this discovery happened, because it matters enormously. The fault segment involved is called Parkfield, a stretch of the San Andreas that occupies a genuinely special place in earthquake science. It's one of the most intensively monitored fault zones anywhere on the planet, packed with sensors. Researchers have used for decades as a kind of natural laboratory to study exactly how faults accumulate and eventually release built-up stress. Despite that extraordinary level of monitoring, some of the fault's most subtle behaviors have remained stubbornly difficult to actually observe, hiding in plain sight within mountains of raw instrument data. That's precisely the gap a team led by Zara Zali and Gregory Barraza at Stanford University set out to close, using artificial intelligence to comb back through years of extraordinarily sensitive borehole strain meter recordings. Instruments installed hundreds of meters beneath the surface, specifically to detect tiny crustal deformations tied to fault slip. What they found, published in June of this year in the journal Nature Communications, was a previously hidden population of what scientists call slow slip. Events, brief episodes where a section of the fault silently slips without producing any felt shaking whatsoever. It's worth understanding exactly why Parkfield became the natural testing ground for this kind of research in the first place. For decades, this particular stretch of the San Andreas has drawn earthquake scientists specifically because of its unusual, well-documented tendency to produce moderate, making it one of the few places on the planet where researchers could realistically plan long-term monitoring experiments around an anticipated seismic event. That decades-long investment in dense instrumentation is exactly what gave the Stanford team the depth and continuity of data needed to train an artificial intelligence system capable of spotting patterns that had eluded human analysts working through the same recordings by hand. The scale of what the AI uncovered is genuinely remarkable. The researchers identified 92 separate short-duration, slow-slip events beneath the Parkfield segment, and 21 of those had completely escaped years of careful manual inspection by trained human researchers. That's not a small margin of error. That's more than 1 out of every 5 events existing entirely outside what scientists believed they already understood about how this specific stretch of fault behaves. 14 of the newly identified events were also independently confirmed using nearby creep meters, a completely separate type of instrument, which strengthens the case considerably that these signals represent genuine physical fault movement rather than some kind of instrumental noise or artifact. After identifying these hidden events, the research team went a step further, calculating where each individual slip most likely originated along the fault. Their analysis found the events occurred at relatively shallow depth and were consistent with the right lateral motion that characterizes the San Andreas Fault system overall, meaning the two sides of the fault sliding horizontally past each other in the fault's characteristic direction. That level of precision, pinpointing not just that hidden slip was occurring, but exactly where and in what direction, represents a meaningful step forward from earlier generations of research that could often only confirm something had happened without clearly establishing the specific mechanics behind it. Here's where the discovery becomes genuinely significant, rather than simply a technical curiosity. When researchers compared the precise timing of these newly detected slow slip events against a separate category of weak seismic signals called low-frequency earthquakes, they found something scientists had never clearly documented before. These silent, slow slip events are systematically followed by measurable increases in low-frequency earthquake activity. In other words, the fault's quiet, invisible movements appear to directly trigger a cascade of subsequent seismic activity, a relationship between two previously separate categories of fault behavior that researchers simply didn't have clear evidence for until artificial intelligence made it possible to detect the full population of hidden events in the first place. As the researchers themselves put it, being scientists, a considerably more complete picture of how faults actually behave in between full-blown earthquakes, and crucially, how stress gets transferred through the crust during those quiet, unnoticed periods. That distinction matters enormously, because understanding stress transfer is precisely the mechanism that eventually determines when and where a fault's locked, stress-accumulating sections finally give way. And this discovery isn't landing in isolation, it's arriving directly alongside a separate, considerably more sobering piece of research examining the broader San Andreas system. A study published in the Journal of Geophysical Research, Solid Earth, led by researcher Liliane Burkhardt at the University of Bern, used a computer model combining historical earthquake records, satellite observations, and estimates of the Earth's crustal rigidity to calculate current seismic strain levels across Southern California. Their conclusion was stark. The San Andreas Fault, segment northwest of Kagan Pass, along with the nearby San Jacinto Fault southeast of that same pass, are currently experiencing the highest levels of tectonic strain measured across the past 1,000 years. The methodology behind that strain calculation is worth appreciating on its own terms, because it represents years of painstaking work rather than a single simple measurement. Researchers had to reconstruct historical earthquake activity across the region using a combination of paleoseismic evidence, modern instrumental records, and satellite-based measurements of how the ground has physically deformed over recent decades. Then feed all of that combined data into a model capable of estimating how much elastic strain energy has been quietly accumulating within the crust itself. That kind of long baseline reconstruction is precisely what allows researchers to confidently say current strain levels exceed anything measured across an entire millennium, rather than simply comparing today's conditions against a much shorter, more limited modern instrumental record. That finding connects directly to something researchers have been quietly puzzling over for years: the fact that California's longest, most famous fault, responsible for some of the most powerful earthquakes in American history, simply hasn't produced a major rupture in over a century. Researchers describe this as the fault having gone unusually, ominously silent, a mystery. Scientists are still actively working to fully explain. There's no single simple answer for why that silence has persisted this long, but the strain data makes one thing considerably clearer: that silence has not meant the underlying stress has stopped building. If anything, the data suggests exactly the opposite. Stress has been accumulating steadily beneath the surface throughout this entire quiet stretch. If you're finding this kind of grounded breakdown of what's actually being discovered genuinely valuable, go ahead and hit that like button. It makes a real difference helping this channel reach more people who want the real science behind these headlines instead of vague, unexplained alarm. Bringing these two pieces of research together paints a considerably more complete and considerably more concerning picture than either study offers entirely on its own. On one hand, scientists have just confirmed, using tools that simply didn't exist even a few years ago, that the San Andreas Fault is quietly, continuously active in ways researchers previously had no reliable way to fully detect, with hidden, slow-slip events directly triggering cascades of subsequent seismic activity beneath one of its most closely watched segments. On the other hand, separate independent modeling shows that key sections of the broader fault system are sitting under more accumulated tectonic strain than at any point in the past millennium. Neither study, taken individually, is predicting an imminent major earthquake on any specific timeline, and it's genuinely important to be honest about that distinction rather than overstating what either piece of research actually claims. What both studies do collectively suggest is that scientists' picture of how this fault behaves and how close various segments might realistically be to their next major stress release has become considerably more detailed and considerably more data-driven than it was even just a year or two ago. That's precisely why researchers describe discoveries like the Parkfield slow slip findings as genuinely valuable, not because they predict a specific date, but because they meaningfully sharpen scientists' understanding of the underlying mechanics driving the entire system forward. It's also worth understanding that slow slip and fault creep aren't inherently sinister on their own. They're a normal, well-documented part of how many fault systems, including large sections of the San Andreas, actually release stress without producing damaging shaking. Scientists have studied this general phenomenon for decades, distinguishing between what they call creep events, occurring close to the surface in the uppermost few kilometers of a fault, and deeper slow slip processes that can sometimes release energy equivalent to a substantial earthquake, just spread out gradually over weeks or months rather than compressed into a few violent seconds. Previous research examining California's creeping central segment even found that portions once assumed to be entirely benign are, in specific locked patches, still capable of producing magnitude 6 earthquakes, a reminder that creep and genuine seismic risk aren't mutually exclusive categories. They can coexist within the very same fault system, sometimes within just a few miles of each other. For anyone living across California or simply following this research out of genuine scientific curiosity, the practical takeaway isn't panic over a specific predicted date, since neither of these studies provides one. It's a deeper appreciation for just how actively researchers are working to understand a fault system that remains, by any measure, one of the most consequential geological features in North America. Tools like artificial intelligence are giving scientists genuinely unprecedented visibility into behaviors that were physically happening all along, just invisible to previous generations of monitoring technology and human analysis alike. That shift toward AI-assisted analysis is likely to expand well beyond Parkfield in the coming years, as researchers apply similar techniques to other densely instrumented fault segments across California and beyond, potentially uncovering hidden populations of slow slip activity in places nobody has thought to look this closely before. At the end of the day, what makes this moment genuinely significant isn't a single dramatic prediction. It's the convergence of two independent lines of evidence, one revealing previously hidden fault behavior through artificial intelligence, the other quantifying historically unprecedented levels of accumulated strain, both pointing toward the same conclusion, that the San Andreas Fault system is considerably more active, more interconnected, and more closely monitored right now than at any previous point in the history of earthquake science. That last point about monitoring is worth sitting with for a moment, because it's easy to read stories like this purely through a lens of rising danger without appreciating the flip side, that scientists' actual ability to detect and understand these processes has never been better. A decade ago, the 92 slow slip events identified at Parkfield simply wouldn't have been visible using the analysis techniques available at the time, not because the fault was behaving any differently, but because the tools capable of separating genuine signal from background noise across years of continuous strain meter data hadn't yet matured to the point where artificial intelligence could reliably do the work. The fault has likely been producing hidden slow slip events like these for as long as it's existed. What's changed is humanity's capacity to actually see them, catalog them, and start connecting them to the broader seismic activity happening around them. If you want to keep tracking exactly how this research develops, along with the real science behind every earthquake headline before it becomes tomorrow's viral clip, subscribe to the channel so you never miss an update. Stay curious, stay prepared, and I'll see you in the next one, ready to break down whatever the strain meters and the AI models reveal next.